21st of January 2022. Welcome to the 10th lecture in Introduction to Lattice Boltzmann Methods. Today we introduce the multiple relaxation time methods. So this will take more than one lecture, but today we will start on this. And content-wise, we'll start with an efficiency consideration. Then we look again at moments, and we distinguish these moments between hydrodynamic, acoustic, and ghost moments. And in the end of the lecture, we come to the classical MRT methods in 2D. Where I should say that this goes with unweighted with an unweighted orthogonal matrix. Okay, so this is what we are going to see. So first, we start with some efficiency considerations. So we learned about the BGK method, and with which we can solve the Navier-Stokes equation, and we see there's convergent. So in principle, we can solve all the problems that we can think about with this one method. I mean, all the fluid mechanics, incompressible fluid mechanics problems. In principle, we can use this method and we are done. Now you may have heard that there are good methods and bad methods. Yeah, so methods that are more accurate or something like this. And now this actually, is not really true, because if you use enough resolution, you get convergence. So all the methods should in principle solve the same equation, so they should all be as good as the others. So why are they different? Well, they are mostly different in regards to the cost. And the cost in CFD simulations is very substantial, or computational fluid dynamics, or colorful fluid dynamics, or something. Colors for directors. Some problem here. Okay, solve this later. So cost of CFD simulations is very high. And depending on your efficiency, different methods have different costs. So we actually have to quantify the cost in order to reduce it. So how to reduce the cost? How to reduce the cost? First, we have to understand the cost. And for this, we have to make a model. So we introduce the computational cost. So the computational cost could, in principle, be different things. For example, the amount of memory that you need. But it could. Mostly we assume that the cost C of a simulation is the time that the simulation takes. And this is, of course, dependent on what you want to simulate. So you have a domain of a size V, which is the volume that you want to simulate. And you want to simulate this for a fixed time, so duration. So duration D. So this is something that comes in time. So cost, volume, and now duration. Now you have your code has obviously a performance, and this performance has to be measured. So we have to introduce a performance measure, which I now call P, and this is given in the Lattice Boltzmann world. It is usually given in node updates per second. And node updates per second, this is called an NUPS. N-U-P-S. NUPS. And this is basically what it means is the wall clock time. So the wall clock time is the time that the clock on the wall shows you how long your simulation takes, divided by how many nodes you have to update, and the nodes that you have to update are the lattice nodes related to the volume times the number of time steps. Okay, I'll write this again as the wall clock time basically is the cost divided by the number of nodes times the time step. And here we use this variables number of lattice nodes n. This is the volume by, so the volume that we have to deal with divided by the grid spacing cubed. So we are assuming three-dimensional simulation in this case here. And the number of time steps, this is T, is the duration divided by what is one time step. So, okay, so this is the performance. So we can rearrange this equation and say that the cost is the number of nodes in the domain times the number of time step divided by the performance. Now we take these guys and put them in this equation, and now we get V times D. So this is our physical problem. Yeah, there's nothing we can change about this. This is divided by P and delta X by the cube and delta T. So this is, now we see how we can influence our problem. So the guys up here, they are the physical problem. We cannot change them. So this is the given problem that we want to solve. So we can improve our method either by improving our coding, or buying a faster computer or something like this so that the performance goes up. Or we can deal with the time step and the grid spacing. And as you see, the biggest influence on the performance is in the grid spacing. So it's actually not really so useful to try to shorten the time step or increase to increase the time step in order to get more performance, because the time step here is only the cost is only linearly dependent on the time step, whereas the dependency on the grid spacing is cubic. So delta x has the largest influence on the cost. So we want to make delta x large, so the cost is low. However, there are of course constraints on delta x and delta t, and of course there are very important accuracy constraints, but we'll not talk about them today. Now we just assume that this is not important. We first here we look about stability constraints most of all. So one constraint is of course the maximum speed. Maximum speed that comes from the so-called CFL condition. CFL condition. And this just says that the velocity in the flow must be smaller than delta x by delta t. So this is the speed at which information travels minus, this is now important because we have a pseudo compressible code, minus the speed of sound. Yeah, so this is the reason for this is that information can only move delta x in delta t on the lattice, yeah, because the lattice Boltzmann method is an explicit time marching scheme. It is subject to such a condition. Okay, this is one condition, and there is another condition which is more stringent. That is the minimal viscosity condition. So we have max speed, minimal viscosity. This is usually the more important one. This is where we now spend our time with. We have to look at the definition of the kinematic viscosity, which is of course a parameter from our problem. Yeah, so the kinematic viscosity is given, and we call it nu. And as we've learned, we can calculate this in lattice Boltzmann by having our theta times 1 over omega minus 1/2, and this goes into delta x squared by delta t, and where we have seen that theta is equal to 1/3. So this is something that we learned from our BGK method. So, and in this, of course, omega is the relaxation rate. And now we can solve this equation up here for the delta x. So we see that delta x is nu delta t divided by theta 1 over omega minus 1/2, and all of this, the square root, which I write as power 1/2. So this is just a rearrangement, and so we see the way that delta x depends on viscosity and delta t and the parameter omega, which of course we can choose freely. Yeah, so so nu, of course, we cannot choose freely. Now we know what delta x is, and we can put this into the cost function. So our cost is then the volume times the duration divided by the performance of our code, and here comes now the with delta x. This is nu delta t divided by theta 1 over omega minus 1/2, and all of this now goes to the power of 3/2, and this again into delta t. So what do we see? So this cost will be minimal, or will actually be 0 if omega is equal to 2. Yeah? So the closer we get omega to 2, the lower the cost. The closer omega is to 2, the lower the cost. Okay, so we want to get omega close to 2. Now let's go back to our BGK equation. BGK collision operator. This is where omega originally comes from, and here we have the Fijk. So I just happen to write it 3-dimensional. You can also write it 2-dimensional, then it would be Fij. The post-collision state is equal to the pre-collision state plus omega Fijk equilibrium minus Fijk. So now let's assume omega would go to 2. So what would that mean? So just we put omega equal to 2 in this, and what we get out is Fijk equilibrium minus Fijk pre-collision state. Yeah, so this happens if we put omega equal to 2. So what does this mean? That omega equal to 2 is the no dissipation limit. So what does dissipation mean? Dissipation means that information that is in the system is being lost. Yeah, so you stir your coffee and you remove the spoon and you wait, and your coffee comes to rest. Yeah, so your coffee forgets the way it was stirred. So for example, your coffee cannot tell you whether you stirred it left or you stirred it right. Yeah, so you stirred it clockwise or anti-clockwise. Yeah, so this information is being lost in dissipation. And if omega is equal to 2, there is no information lost. So you have no dissipation. No information is removed from the system. So why do I say this? Let's look at this again. So say we have, this is the post-collision state, F asterisk ijk, and this is supposed to be 2 Fijk equilibrium minus Fijk. So what goes into the collision is Fijk. What comes out of the collision is Fijk. asterisk ijk. However, you can also rearrange this and see that Fijk is equal to 2Fijk equilibrium minus Fijk before collision. So what does this mean? This means you can run the simulation the same way forward as you can run it backward. Yeah? Forward collision is the same thing as backward collision. So you only have to invert the direction of the streaming, and then you can run your simulation backwards. And if this worked, this would be very interesting, yeah, because this would mean that if you have your coffee steered, and then you left it to its own device until it relaxed, which of course it wouldn't because there's no dissipation. But in principle, you leave your coffee, and then you take the state of your coffee later, invert all the directions, and then your coffee returns to the way you steered it, which of course is not possible, yeah, because it means that the simulation has to remember its entire history, and this is not, usually not stable. It would be nice if it were, but it is not. So this is not possible. So let's write down here, this is a perfectly reversible collision. For omega equal to 2. Now, as we say, it's not plausible that simulations can do this, and in fact what we observe is that in the BGK equation, omega larger than 1.9 or so often leads to instability. So your computer will tell you, I can't do this. Yeah, I cannot remember everything about the past. So I will now crash here. Yeah. This is the simple message. Okay, now we have this problem. We want to get with omega as close to 2 as possible, but in the BGK equation, we are stuck with a value quite below omega, equal to 2. Now the problem, or the challenge is there a way to get closer to 2, to get omega closer to 2, without losing stability? And what we have to do in order not to lose stability for omega equal to 2, or being closer to 2, is of course to add some dissipation that helps the system to forget information that is not important while keeping information that is important. And for this, we have now to dig into, again, into our asymptotic analysis to know what information is important and what is not important. So we recall our asymptotic analysis from, and this is from lecture 6. And here specifically, we go to equation 6.6. So you can look this up later if you want. So in this equation, we talked about the 2D leading. So this was in 2D and it was leading to the Navier-Stokes equation. So it was one step before we arrived at the Navier-Stokes equation for the momentum. So this equation, basically, it is the Navier-Stokes equation. We just didn't put everything into it yet. So this was the time derivative of the first order moment m10, the thing to first order, and this plus the spatial derivative m of m, the second order moment, with a bar, plus this, the other spatial derivative of the moment m11. And then there was this omega here, which we identified with the forcing term, and for this discussion now, we just assume that this forcing term will be ignored. We set this to 0. Now, in order to get to the Navier-Stokes equation with this, we had to identify the moments with the primitive quantities. So this m10 first order was, of course, rho to the 0 order times u to the first order, and m20 second order was m20 equilibrium second order minus 1 over omega minus 1/2. So this is where omega gets into the system. And here was capital omega 20, and this is to first. No, it must also be to second order. To second order. And we have m11 second order is m11 equilibrium to second order minus 1 over omega minus 1/2 omega 11. So this is how we derived the Navier-Stokes equation from the BGK method, and we see that this relaxation rate omega enters the system here, and what is specific to the BGK methods is that there's only one relaxation rate. So BGK means that omega, there's only one omega, and this acts on all moments. Now the point here is that even though omega acts on all moments, what we observe here that the Navier-Stokes equation depends only on the omega in these two moments and not on the omega in all the other moments. And this obviously leads to the obvious question why we are not relaxing the other moments with a different relaxation rate. So why not relaxing moments with different rates? Okay, so this is basically what we are going to come to. So now, before we come to this, we still have to identify. We still have to identify these guys, yeah. And these guys are as follows: omega 1 to second order. Yeah, so this is everything has been derived in the lecture number 6. So this is just, I write them down. This omega 0, 2 is dx u1 rho 0 plus theta dy v1 rho 0. Okay. Now there's one important thing to note about this guy here. Namely that there is the x, here we have the x derivative of the x velocity, and we have the y derivative of the y velocity, but with a different prefactor. Now, if we, so obviously if there's an omega 2, 0, then there's an omega 0, 2, which behaves in the same way. And when we add these two things together, we get the following, namely we can put in front of this 1 plus theta rho 0, and this goes into dx u1 plus dy v1. So, and can anybody tell me what this here is? Okay, nobody. So the guys on YouTube said something strange. So okay, you can't tell me what this is. So this is the divergence of the velocity. Yeah, so if it's the divergence of the velocity, this guy here is 0. And if this guy here is 0, this means that the relaxation of this guy does not show up in the Navier-Stokes equation. Okay, so we just identified that the moment m20 plus m02, their relaxation rate, it is not important for the Navier-Stokes equation. However, yeah, okay. So at least to leading order, this is where we are looking at. So, however, if we look the other way, because we are not interested in omega 20 plus omega 02, but we are actually interested in omega 020. So we have to use the other combination 2, which is omega 20 minus omega 02. And this is, of course, not 0, because it looks like this dxu1 minus dy minus dyv1. So okay, this guy here does not vanish. So what does this mean? This means that only the relaxation of m20 minus m02 is of influence to the leading order. And this requires us to make a regrouping of our moments. So there are these moments m20 plus m02, which we are going to relax with an omega p. And there is the moment m20 minus m02, which we have to relax with the relaxation rate that belongs to the Navier-Stokes equation, which we called omega. So, and this finally leads us to the grouping of moments, and this now for D2Q9 lattice. So this of course has to be done for each lattice individually. And in this model we have of course 9 different distributions. So we have 9 different independent moments. And they are now grouped like this. So we have M00, M10 and M01, and these are the conserved moments. So they do not change in the collision. In BGK, this is done by having their equilibrium being equal to their pre-collision state. Then we have M11 and M20 minus M02. And these are the non-conserved hydrodynamic moments. So they are called hydrodynamic moments, and because we need them for the Navier-Stokes equation. They appear in the Navier-Stokes equation. And okay, so we have now taken out not the moment M20, but the moment M20 minus M02. And this means we have another group of moments which contains only one, namely M20 plus M02. And this actually can be identified with the pressure. And this we call an acoustic moment. So the incompressible Navier-Stokes equation where we looked at, this assumes there's no sound wave. And actually this guy here is the physical reality of a sound wave. So this is the pressure. Pressure oscillations go in this moment. And this omega p, which we now use to relax this moment, this is related to the so-called bulk viscosity. And what it does, it allows us to, or it regulates the damping of acoustic waves. So why is the bulk viscosity called the so-called bulk viscosity? The bulk viscosity is so-called because in different parts of literature, bulk viscosity is defined in completely different ways. They always mean something like the same, but the details of the definition are always different, and so it is very difficult to communicate about this subject, because you first of all, you always have to make clear that both of you have the same definition of the bulk viscosity, and there are different definitions of the bulk viscosity out there, but we'll do not cover this in this detail here, that this would matter to us today. So now we got something like 6 moments. This means there are 3 moments left, and these are of course M21, M1 and M12. These are of course third order moments. And we see that these are not appearing in the Navier-Stokes equation to leading order. So we define a relaxation rate omega 3 for them. And we have M to 0. And this is, of course, the fourth order moment. There's only one of them. And we give them the rate omega 4. And these moments here, they are neither conserved nor hydrodynamic. These are called the ghost moments, because they are here somehow, but they are not part of the Navier-Stokes equation. Okay, so now these are the moments. So what we see is we have to relax 2 moments, namely these here. They will have the rate omega. Then there is one that comes with the rate omega p, and then there's one with the rate omega 3 and one with the rate omega 4. And the one with the rate omega p, this is related to sound waves. So let's talk about the suppression of pressure waves in the simulation. And the disclaimer to this is, of course, you are supposed to do this only if you're not interested in acoustics. Yeah? So suppose you are not interested in acoustics. So if you want to solve an acoustic problem, then of course you're not supposed to suppress pressure waves. And in acoustic problems, you also have to use, of course, acoustic scaling. But if you're not interested in acoustics, then what you would usually do in order to get convergence of your method is to use diffusive scaling. As in our asymptotic analysis, and diffusive scaling, of course, means that delta t is something proportional to delta x square. and there's a speed of sound. Cs is equal to the square root of theta delta x by delta t, which is of course 1/3 delta x by delta t. Now in this diffusive scaling, what you usually do is you use an artificial Mach number, so you are not interested in what is the Mach number of your physical problem, but you assume the Mach number is very small, and now you can use an artificial Mach number going to 0. So artificial Mach number, this we get by looking at the limits delta t equal to 0 for the Mach number. This is the asymptotic limit, the time step going to 0. Under this constraint that the time step is proportional to the grid spacing square, which then means that delta t equal going to 0, use the s, and if you put the speed of sound into this, you see that the Mach number goes to 0. So you let your Mach number go to 0. So, and in this setting, acoustic waves are just regarded as noise. I think that acoustic waves is where the word noise originally comes from. Yeah, so they are a noise in a computational sense that we regard them as errors. Yeah, they are not supposed to be here because we want to have a zero Mach number, and in a zero Mach number, acoustic waves travel infinitely fast, and so they will be gone in an instant. Now, what we can do without going too much into detail here, in order to get these things removed, is to specify omega p in a certain way. Now, we said that this relaxation is about losing memory, yeah, and you lose most memory, or you lose your memory quickly if you put omega p equal to 1. Because what does it mean? You put omega p equal to 1. Omega p equal to 1 means that in each time step you relax your system towards equilibrium. So whatever information there was out of equilibrium is removed from the system. Yeah. So, and if you do this, this usually leads to quick dissipation. So omega equal to 1, or say, okay, let's say close to 1. Yeah. So this leads to quickly dampens acoustic waves. So, and this is a way you can remove them. And this removal of acoustic waves often also improves stability of your method. And by improving stability, you may be able to increase the omega for the Navier-Stokes equation to a larger value, which means you can increase your efficiency. So this was about omega p. Yeah, and then there's the other ones, omega 3 and omega 4, and they are the ghost moments, and they can also be suppressed by a similar way. So the suppression of ghost moments. So there's also information in these ghost moments, but these ghost moments are not related directly to the solution of the Navier-Stokes equation. So let's write this down. The ghost moments M21, M12, and M22 they have no influence on the leading order solution, which means we can in principle do whatever we want. And by the same argument that we just had, we can say that ghosts can be suppressed by setting omega 3 and omega 4 close to 1. So there is, of course, a lot of discussion in the literature whether this is always the best idea to do this. No, it's not always the best idea, but it is one that is very often chosen and which also kind of works. So having said all of this, we come to the classical MRT methods. Classical MRT model. And for this, so this was introduced by Lallemande, Pierre Lallemande, and Li-Shi Lu in 2000 in Physical Review E61/6, and this was on page 6546, yeah. And this is about the T2Q9 model. So of course there is there are many three-dimensional and other models, but this is the very simple one here, and the one that you may also be interested in, for example, for using in your project if you want. This would be a possibility. So we talked a little bit about the idea, and now we talk about the practical approach. Yeah. So as what we have seen is that we want to relax moments with different rates. And for this, first of all, we have to compute actually the moments. So this method requires a transformation from distributions to moments. So by the way, why do we still need distributions? Why can't we just do everything with moments? Is anybody listening, and can we tell me why we need this still need distributions? I never get a lot of feedback in this lecture. This is my trouble. I would have done more exercises if I see more feedback. But without feedback, I only can give lectures. Yeah. So if you ever wonder why we don't do exercises. Okay, we still need the distributions because we cannot stream moments. Yeah. For the moments we need for the streaming we need distributions. For the relaxation we need now the moments. In BGK we use in BGK the distributions are used both for the collision operator and the streaming operator, but in the MRT methods, yeah, because we can only relax moments, we use moments for the collision operator and we use distributions for the streaming operator. Okay, so how do we do this transformation in this method? We do this transformation by using a matrix. I'm not going to write down the matrix. You just get the basic idea here. So I write this matrix with these two underbars, and we write the transformation like this. So we have a vector of moments, which I now write with a small m because the large M is already given for the matrix. So this is the moment vector. So this moment vector is equal to the matrix times the distribution vector. Yeah, and as you see, there is they use a different notation from what we are using. Yeah, there is a vector notation. So this vector is a one-dimensional vector, which means there, if you want to have the parts of the vector, there will be one index. Yeah, one index here, fi. This is different from, if you will, the Gaia notation. So Gaia would write Fij, yeah, for having one index per spatial direction. So this Gaia notation, this can of course not be put in a vector as the vector notation. However, the Gaia notation, in the Gaia notation you have it is always clear how the f's are arranged, where in the vector notation you have to have an agreement in what is f1, what is f2, what is f3, and so on and so on. Whereas in this fij, so this I here, this is an element of 0 to 8, and in this version here they are elements of -1, 0, and 1. Yeah, so this makes it completely clear how they are arranged, whereas in the vector notation you have to have an arbitrary agreement of the ordering of the distributions. Okay, but this can be done. So we have the transformation. Then we need the collision after the transformation. So this collision looks like this. We have an M after collision vector is M before collision plus a relaxation matrix times M EQ, the equilibrium of the moment, minus M. And this relaxation matrix contains the relaxation rates on the diagonal. So what you could also write, it is the diagonal vector matrix times a vector of relaxation rates. Yeah, so this is the diagonal relaxation matrix. Okay, now you do your collision in terms of moments, and then you have the back transformation where again you need F asterisk, and this is equal to M. Now we use the inverse of the matrix to get from the moments again the distribution. So we first have to specify the matrix, then we have to compute the inverse of the matrix, and then we can actually apply all these transformations. And then in the end, as I previously said, we do the streaming, and the streaming has to be done in terms of distributions. So the streaming would be that Fi x plus Ei, so this is the direction corresponding to the index I. In the next time step would be Fi, so this is the pre-collision state, is the post-collision state here at the location here and in the previous time step. Okay, so what I said before, so this is really important to remember. MRT means streaming distributions and colliding moments. So in comparison to BGK, of course, which also has streaming distributions and colliding also distributions. This is why you need more steps here. And this is, of course, also why MRT is kind of more expensive in regards to how much operations you have in one lattice update. Okay, so we did not specify this this matrix yet. What the classical, so the classical is the one by Lallement and Liu. The classical MRT method uses an orthogonal matrix. And of course, it requires a specific ordering. So depending on the ordering of your moments, your matrix will look different, yeah? So you have to make sure you know how you arrange things. There's no unique way of doing this. So in this setting, the moments behave a little bit different from the way we learned it in this lecture, because these moments are not countable anymore. Unless you say, okay, I count them, you know, it's the first in the matrix and the second in the matrix and the third in the matrix, yeah. In that way they are still countable, but this way of putting this is the first, the second, and the third moment in the matrix, this is a completely arbitrary ordering. So in our definition of countable moments, we count them according to their order, yeah, and this is not the case if you put them in this way into a matrix. So let's look at how did Lallement and Liu actually arranged them. So the D2Q9 moment system of Lallement and Liu. So of course this is pretty arbitrary, but this is the way they did it. So M consists of the following. So there's of course 9 moments, and the first one is the density rho. Then there's a thing called E. Then there's a thing called epsilon. Then there is Jx. Then there is Qx. Then there is Jy. And there is Qy. And then there is Pxx. And then there is Pxy. So not only is the ordering of these moments arbitrary, but the naming is also arbitrary. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are, you know, our eight moments. Okay, instead of writing down the matrix, which you can do as an exercise, I give you the definition in our countable moments. So this is of course now just a linear transformation. Yeah, we have our definition of moments, which are the countable moments, and they have this kind of arbitrary definition, and this looks like this. So rho, you could guess what rho is. Rho is M00. This is a conserved moment. So here actually this is the one that is equal to the countable moment. There are 3 moments which are equal to countable moments. So this is conserved, obviously. So now they are not continuing on with the first order moment, but they are continuing with something like a second order moment. So what they define as E is 3 times M m20 plus m02 minus 4m00. So what kind of moment is this? This is actually an acoustic moment, or the acoustic moment in their setting. Then they have epsilon, and they define epsilon as 4m00 minus 6 m20 plus m02 plus 3m22. And this is a ghost moment. By the way, what you observe here is that this sum contains moments of different order. So this here is the zero order moment, this is the second order moment, and this is a first order moment. And they sum them together and get an epsilon. So the question is epsilon now a first order moment, a second order moment, or a zero order moment? Yeah, this is not defined in this setting. Okay, going on to Jx. So Jx is the momentum. Yeah, this is m10, and this, of course, also is a conserved moment. Then they go on with a third order moment, or something like a third order moment. This is Qx is equal to 3m12 minus 2m01. This is a ghost. Then they go on with the momentum in y direction. So this is m01. This is again conserved. I really don't get it why they put it in this random order. Then we have Qy is 3m21 minus 2m. Oh, wait. I made a mistake up here, sorry. So here in Qx, this is m10. I have written m01, but it's m10, yeah? So because I missed the line. And here down here is m01, and this again is a ghost. And then we have Pxx, which is m20 minus m02. And we have Pxy, which is m11. And these are, of course, guys that we know. They are the hydrodynamic moments. Okay, so these are all the 9 moments expressed in in terms of raw countable moments. So why do they look so strange? Well, the moments here are chosen. So apparently they had some idea behind this. They are chosen to be orthogonal with respect to the unweighted scalar product So we discussed what orthogonality means already. Yeah. So we have m. So we have a moment m phi. Yeah. Some moments. Yeah. Which again I write here for my convenience in terms of the countable moments. So ij from -1 to 1, and then there is a kernel phi ij into fij. And then there is another moment, mc, or psi, and this is ij equal to -1 to 1, phi ij fij. So the unweighted orthogonality. Unweighted orthogonal means, this means that the sum over ij from -1 to 1 phi ij times psi ij, this sums to 0. Then it's unweighted orthogonal. So, example. Let's look at this moment E. This moment E is 3m20 plus m02 minus 4m00, which we can translate in the sum here. Ij equal to -1 to 1. So then this kernel function must be related to 3 times this moment, 3 times this moment. This is I square. Then we get to this moment plus j square minus 4. So because this here has no prefactor and this goes into fij, which implies that the phi ij is equal to 3i square plus j square minus 4. And the other guy, rho I and j from -1 to 1 is 1 times fij, which means that psi for this moment is ij, and phi ij is equal to 1. Yeah. So every time we multiply just by 1. So, and if we now take this scalar product fij from -1 to 1 from phi ij times psi ij, what we get is ij equal to -1 to 1, and we have 3 times I square plus j square minus 4, and this we multiply by 1. And now we have to see how many times do we have I and how many times we have j. We have these things 6 times. So what we end up with is 3 times 6 plus 6 minus 4 times 9. And this, in fact, is equal to 0. So then this is unweighted orthogonal. Okay, and you can check this for each combinations of these moments, and they are all unweighted orthogonal. So why is this done this way? So the reason why it's done this way is that there are some people, so this is completely subjective, some people consider orthogonality of the moments very important. And if you go really to the bottom of it, there is something true to this, but not in the way it is done here, unfortunately. Yeah. So the reality is nobody. I mean, I've talked to these guys who invented this a lot of times. Nobody can say why, and especially not the ones that introduced this. So especially, okay, Lallemont is 80 years old. I don't know whether you are able to hear some of his lectures nowadays, but Li Shilu, when you're listening, yeah, maybe, I mean, I told him many times, Li Shilu is not listening to my lectures, so he thinks he knows everything about Lattice Boltzmann, of course. They love to talk about orthogonality, but they cannot explain why they think this is important. So let's spend the last 8 minutes in starting a discussion on this. We're not finishing with this. So if you want to know, you have to listen to the forthcoming lectures. I think the next and the one after this to actually get closer to the bottom of this. I don't know whether we get really in the to the solution, because this is a complicated problem. Obviously, if the big shots in the field just can't answer this question. So, does orthogonality matter? We simplify the question today by saying, does it actually have an effect? So my spoiler here is, it sometimes matters, but often it doesn't. Okay, let's look at 2 examples in the last 7 minutes. Let's start with the third order moment, or related to the third order moment, Q and their relaxation. So Qx after collision is Qx before collision plus what they call omega 5, Qx equilibrium minus Qx. Yeah, so this happens. This is one moment collision in the Lallemont and Liu model. Now what we can do here is we can put the countable moments into this equation and see how this behaves. So this Qx is 3m12, which is of course now the post-collision, minus 2m10 post-collision. So this is the transformation between Qx and the countable moments. So we have to do this on the other sides too. So we get here the pre-collision m3 times m12 minus m10 plus omega 5. And here comes the equilibrium of 3 times m12 equilibrium minus 2m10 equilibrium, where we have to subtract the non-equilibrium part, minus 3 times m12 plus 2m10. Okay, so this is the same equation just expressed in countable moments. And here we have 2 different moments, and especially we have here this moment m10 everywhere, and m10 is of course a conserved moment. What does it mean as a conserved moment, m10? is a conserved moment, and it's conserved exactly then when the post-collision is equal to the pre-collision is equal to the equilibrium. Then it's conserved. So now, because it's conserved, you can replace it here everywhere. And if you replace it everywhere, what you see is that this guy, oh wait, here's a 2 missing. So this guy and this guy cancel out, and this guy and this guy cancel out. So, which means in the end, this leads to 1, 2 post-collision. M12 post-collision is M12 plus omega 5 M12 equilibrium minus M12. So in that case, orthogonality and non-orthogonality doesn't make any difference. Yeah? So you do exactly the same as if relaxing raw countable moments. So no need for orthogonality in this case. However, this was a special case, namely that the only moment that appeared here, a part of the moment M12, was a conserved moment. So let's look at a different example where we have a mixture of moments which are both not conserved. So different example. Namely, so I call this now equation 10.1 and see whether I get this in time. So this is the moment epsilon, and epsilon is equal to epsilon before collision plus omega 3 epsilon equilibrium minus epsilon. So now this is a bit longer. Yeah. So this is for the replacing epsilon by its raw countable moments is 4 times m00 minus 6 m20 plus m02, and you see these guys here are not conserved, so they make the difference. 3 times m22, and this goes on the other side, so I have to write a little bit here. Hopefully I'll manage this in the next 2 minutes. Minus 6 m20 plus m02. And this goes into, this has plus 3 times m22. Plus now comes the relaxation part is 4 m00 equilibrium minus 6 m20 equilibrium plus m02 equilibrium. So this is a long equation, plus 3 m22 equilibrium minus 4 m00 plus 6 m20 plus m02 minus 3 m22. Okay, so that's all of this. So one of these moments, namely m00, this is a conserved moment, so this will simply cancel out of the entire equation. Yeah, so this will all cancel out. That's all going to cancel out. However, there is one part that's not going to cancel out, and this is now the equation 10.2, and this is m to 0 post-collision 02. So this is actually what they have as m00 no, not SM, is P, how did they call it? PXX. Okay, I don't know why this is called. Okay, so this is, okay, I've forgotten what this was called. So this is M20. Yeah, this is E. This is what they call E, right? So M20 plus M02 is M20 plus M02 plus omega 2, M20 equilibrium plus M02 equilibrium minus M20 minus M02, and we put this into 10.1, and if we do this, which I now skip over a little bit, then we get that M22 after collision is M22 plus omega 3 into M22 equilibrium minus M22 pre-collision minus 2 M omega 3 minus omega 2 times, I have to go to the next line, times M22 equilibrium plus M02 equilibrium minus M20 minus M02. So I'm a bit over time, but I only have to write down one more sentence. So the composition of moments influences, in this case, where we have where we have a mixture of non-conserved countable moments. So the composition of moments influences the relaxation process if omega 3 is not equal to omega 2, in BGK this would be the case. And this, no, okay, I have to write two sentences. In this case, that this can cause difficult to understand problems, and this is what we talk about next week. So the lecture is now over. Sorry for taking 2 minutes more. Okay, yeah, okay, now I took 3 minutes more. Okay, thank you for listening. Yeah, we continue here in this place in the next week, and yeah, stay safe and see you next week. Thank you for listening.